Good afternoon, everybody. Thank you for your patience. Sorry for starting a little bit later. As always, the law of Murphy comes in when you organize a workshop. So I would like to welcome all of you at this PVB workshop with the title PVB, a boost in the recycling. It's a workshop organized under the Sunrise project, which is a research project working on the PVB layer that can be found in between of laminated glass. And we have quite an important agenda today. And as we start a little bit late, I would just suggest we start quite quickly. Maybe present myself. My name is Olivier de Weert. I'm the Secretary General of the European Glass Recyclers Association. We, as Verver, we decided to participate to this research project because it's important for us as glass recyclers to have a solution for the PVB, which is in between the laminated glass in windshields. And this discussion is even becoming more important because at European level, we are currently discussing the dismantling of windshields in which you have laminated glass and hence PVB in end-of-life vehicles. And as it appears, there might be an obligation of a mandatory dismantling in all end-of-life vehicles under a future regulation on end-of-life vehicles. As Verver, we of course support this dismantling obligation because it also opens a lot of perspectives for the future for recycling of the PVB, which has actually, when it can be recycled, a higher value than the glass itself. So I would like to start by announcing our first speaker, which is who is Angelica Perez of Loredera. Loredera, who is also the project manager of the Sunrise project, and Angelica, who is a chemical engineer and who started already working at Centro Tecnológico Loredera in 2009. Is now has been the program manager of the Sunrise project. So, Angelica, warm welcome to you from Spain. I would like to invite you to give us a short presentation of the Sunrise project, which is, I think, in its last month now, and its status. I will give you the floor.
Olivier, for the introduction. I will share my screen in order to start my presentation. I think you can see this.
Yeah, I can see you.
Okay, perfect.
If you could just put it maybe on speaker modus, Angelica, because it's still on an internal modus where you can see all the slides. Yeah.
Now, okay.
Thank you.
Okay, so thank you very much for organizing this workshop and giving the opportunity to present the Sunrise project related with the recycling of polyvinyl butyral from laminated glass. And this is my introduction. Olivier has already introduced myself. I work in Loredera Technological Center since 2009, and I work as European project manager in the center, coordinating and preparing proposals and coordinating projects under execution. So this is, in this case, Sunrise project. And when we start to introduce the project, we always start with the main problem to understand which is the main problem of PVB. Probably most of you know about the problem. You will know more in the next presentations, but for new attendees for this workshop that have not followed the project, I think this is important. So, I will. So PVB is a plastic material which is found in laminated glass. Is the main application of PVB is in laminated glass and is used as a safety polymer to avoid the break of this glass easily. So here the main problem or the main waste is not the PVB, it's the laminated glass. So this is a problem that, okay, because laminated glass currently is recycled. This is in the value chain of the recyclers. The recyclers collect this waste from different sources, from automotive or from construction, but only for recovering the glass, and PVB is not considered, is not the focus of the recycling. So this is a waste in the glass recycling process. And up to now, there is a limited recycling of this material from the glass recycling value chains. Most is incinerated or landfilled. So this is the main problem. Okay, these are volumes of glass waste and PVB. And one of the issues is that PVB is not so much used like other plastics, like other more common plastics like PVC or like polypropylene, polyethylene. But if we compare, for example, with PVC, the environmental footprint could be bigger. So the issue is that there is a problem, but at least this polymer is collected in the value chain. So we have the opportunity to make something with this polymer. So according to why this PVB is not recycled, there is different challenges in the reusing of this plastic. On one hand is that this PVB is contaminated with glass, which makes difficult to recycle this PVB again in optical applications, because this glass or these impurities provide haze and turbidity. Then also there is another problem that in the recycling of laminated glass, this PVB is exposed to outdoor conditions, which also degrades the polymer. And the third challenge is the variability of PVB. There are different types of PVB, different plasticizers, different functions and configurations, which makes that we cannot in all the cases mix different types of PVB, because could degrade the final properties depending on the application. So this is why Sunrise project was originated. This is the reason why this project was originated. And the main objective of the project, according to this title you can see here of the project, is to develop a multi-sensor sorting tool in order to make a circular recycling of the PVB again in applications like laminated glass. Here in the project we work in construction and also in automotive glasses, waste glasses, and this project is most finished. Okay, this project started in June 2021, so we have been working 3.5 years, and we are in the last month of the project. So most of the results we are going to present today, although there are some aspects that are still working on, and this is what we want to present today. Okay, this is the structure of the project. This is only in order to have a visual image of what we have been working in the project. We have been working on one hand, okay, we have been from the beginning contacting with the recyclers, and the most principal part of the project was related after having the waste and characterize the waste to develop this sorting tool I will explain after that. This sorting tool which allows to classify the PVB within the laminated glass according to different aspects of composition and degradation. This was the main work in the project at the beginning, working these methodologies in this sorting tool. And then we have been working in treating these classified PVBs by a mechanical and chemical process in order to increase their purity and remove the glass. Now, in this last part of the project, we have been working in translate these PVB, recycled PVB flakes in different formats in film and dispersions, dissolutions, and pellets for different applications that I will explain again in the laminated glass sector, in energy sector related with batteries, and in others like coatings and textiles. So now I will enter directly in the results of the things the project has been working on and the results of the project. On first place, as I have mentioned, the main focus of the project was to develop this multi-sensor tool. This sensor was aimed to have a full laminated glass and without break it, analyze the PVB inside and evaluate which is the degradation status according, in this case, to haze or yellowness aspects, and also identify composition in terms of identify if it is PVB or not, and also the type of plasticizer. So this multi-sensor sorting tool was developed based on spectroscopy techniques, based on Raman and NIR for the composition, and in an integrated proof head which analyzed haze and transmittance and yellowness aspects. Okay, in the project we have been developing a prototype. It's a small prototype, but allows to verify that this classification can be done and allows a classification of 100 laminated glass per hour. And according to the accuracy, it has been one of the aspects is that it has developed a new method to detect the haze that can be done online, and with an accuracy of 1% points in the prediction of this haze. Okay, this sensor, which is this part of here, this is the multi-sensor module, has been coupled with different systems, because in the project the idea was to demonstrate this can make a demonstration, a continuous demonstration of recycling laminated glass waste. So this was coupled to a preparatory module, which was a cutting module, because the prototype in the project allows a small dimension glass. But the idea should be that we could have, for example, a full windscreen and put in the sensor. And this is also coupled with a cleaning module to clean the area where the sensors can measure. And then this multi-sensor detects the category and the actuator, which is this part. This actuator is linked to a belt, a conveyor belt, where it's moving its glass in each category for storage. So I have already mentioned something about the sorting categories, but okay, to clarify, as I mentioned, we have identified different categories. One first category, which is, okay, we have defined category 1 and category 2, which are both PVB. Category 3 is not PVB. And in this case, the methodologies we have developed based on NIR and Raman allows both very good prediction in is PVB and it's not PVB. Then we have discriminate between category 1 and 2 depending on the quality, the degradation, according to the yellowness detected by the sensor and according to the haze. Here also the prediction is good because it's directly measuring the haze and the yellowness through transmittance values. And then we, within category 1, we have discriminated aspects related with composition, related with type of plasticizer and composition. Here we have been, obtained better results with Raman sensor, because in the case of NIR, there could be more errors between some type of plasticizers and between the minor plasticizers. These sensors for this prediction were coupled with algorithms, with training algorithms. So the methodologies developing the project involved to put a lot of data, known data of laminated glass with PVB. And based on this data, the partners have developed algorithms, prediction algorithms, that have trained and predicted the final category. So this is related to the sensor. Then this multi-sensor tool has been implemented in two different demo locations, one in Spain here in Lurederra, and one in Italy. In Lurederra has been included the full system, this multi-sensor tool that I have showed in the previous slide. And this is installed in the location where we have also a mechanochemical pilot line for the purification of PVB from glass. So these are the images of the pilot line we have been using in the project for the posterior mechanochemical recycling. And basically what we do in this treatment is mechanically separate the glass from the PVB, and then with a chemical treatment in different washing steps, try to remove and break the 16 bonds between glass and PVB to remove the other PVB, the other glass to the PVB, sorry. So here in the project, this is some examples of some batches we have treated of sorted categories. For the case of the high quality category, category 1B in this case, which was triethylene glycol oligoester plasticizer. And okay, these are results about the inorganic contents, basically glass. We have after the mechanical treatment, and this more important, after the chemical treatment. So we are mostly below 0.5% of glass in the final PVB flakes. So this is regarding the first part of the project. Then, as I mentioned, the project needs to transform these flakes in different products for the final applications. The main application of the project, what we aim in the project, is going to the same application, which is a more challenging one because it requires optical quality. And in this case, what we have been done by the partners first is they need to transform these flakes in order to obtain finally a film, an interlayer film for the laminated glass. We have been working in transforming in pellets and also after that in film. What happened here that in this process of extruding the PVB, there are going to be a new thermal degradation, and also in the posterior use there could be this thermal degradation. So the partners have been working in antioxidant additives to avoid the chain extinction mechanisms, which is created by the thermal degradation, inhibit this and allow a new life for this PVB. So here, working with very low quantities of antioxidants, it has been possible to inhibit this degradation, and this has been also done in pilot scale with antioxidants, including in this production of pellets for after that film. So this is the film production and lamination process. Okay, from the pellets we have been working after that in film. Here the main outcomes of the main conclusions of this work has been, on one hand, the cleanliness of the mechanochemical treatment which has been developed results in a cleanest PVB that it's was compared with other recycled PVBs in the market, and in terms of transparency was higher. But this was not enough. When we go to process a new film for laminated glass applications, we in the end, even we have better results than current in the market, we need to mix with virgin PVB in order to reduce aspects related with haze and yellowness. So this, in the project, we have been working in mixtures of virgin and recycled PVB, and we have been able to produce these films. And if I go to the applications in laminated glass, we have been working in different applications. On one hand, for construction glass, for laminates with Ariño, and with PV panels with MET. company. Here, in the case of laminates for construction, we have here some results we have been obtained in terms of transmittance, haze, yellowness, and inorganic contents. So what we have been done in the project, we have been working with these mixtures of virgin and recycled PVB, and we have compared. In this comparison you have here, this is compared with a virgin film, but this virgin film has been reprocessed. Okay, so because when we compare, if we compare with virgin film as it is just processed once as a product, these values of haze are lower, of course, and these values of transmittance are higher. But we would like to see in this comparison how the recycling, the part of recycled PVB is affecting in decreasing these values or worsening these values, and what is due to the recycled material and the possible impurities, and what is due to the reprocessing itself of a polymer. Okay, because when we make this virgin recycled mixture, we are reprocessing again the virgin PVB together with the recycled one. So this is the comparison that is here. And in terms of transmittance, of course, we are lower, and in terms of haze, we are a little bit higher. Also for yellowness, we are a little bit higher. But what we will, when we compare this with the virgin PVB without reprocessing, what we see is that most of the increase in haze, most of the worsen of the properties is due to the reprocessing of the materials, which also can involve some impurities in this reprocessing. I mean, we are not working in clean conditions when we make these films, so this is something that can affect. What I want to say here is that these values are not bad at all, because if we could translate this in a really real production facility of PVB with the good facilities in terms of extruders and film and gas extrusion machines in clean conditions, this could be even better. In the case of PV panels, what we have is values related with comparing EVA, which is current use encapsulant, with commercial PVB and with recycled PVB. Here we see that in terms of transmittance, there is not so much difference regarding EVA. So in terms of transmittance, PVB could work. In the case of adhesion, we have had some problems, but again, we have to see if these problems are due to lack of homogeneity in the processing of the film, or it is due to the really the characteristics of the PVB. Okay, this was the main application. Now I will go to the other applications faster.
Angelica, just maybe an administrative information. You have 5 minutes left for your presentation.
Okay, yes, I will go faster with this. So for the other applications, only to mention the applications we are now developing. These are applications in which the quality regarding optical properties is not so big, so it is not so challenging. And one of these applications is pillable coatings for construction. Here the company Vadex is applying the PVB. In this case, what we have been working in the project is make dispersions to apply this in coating formulations, so different format like than film. The other applications related with coatings on textile sector. Here there has been 2 applications, one for coatings based on recycled PVB for UVA protection. Here the Next Technology Textile Center in Italy has been working in this application, and they have found good results in the use of PVB even without the UVA absorber, could protect from ultraviolet radiation, but in increasing this with inorganic or organic ultraviolet absorber, the results has been good. And in the case of the carpets, the results has not been so good, but this could be related with the format preparation. Here we have been working with the solutions of recycled PVB. So the results in terms of adhesion has not been good. And we think that probably working with dispersion, this could be better. Finally, the last application we have been working on is related PVB in as binder and polymer material for separator in batteries. Here we have been working in mixtures, in the case of binder, substituting PVDF in 20% to 50% concentration, and there has been good results with the 20%. There is no detriment in the binder functionality. And also for polymeric separators, there has been good results using membranes. This probably could be limited for some type of windows, of voltage windows, but there has been also good results using PVB as separator here. And finally, for the environmental aspect, because the project, at the end of the project, is compiling all the results in terms of the recycling process, but also in terms of the application and substitution of these products. And we have been working in environmental aspects and economical ones. We have not the final results about the application side, but about the recycling process, we have demonstrated that, of course, the PVB recycling is better when we compare with other scenarios of incineration or landfilling in terms of environmental aspects, in terms of carbon footprint reduction, and also in terms of other categories like more related with toxicity. And related with the economic outcomes, again, we compare these scenarios with incineration and filling, which suppose a cost. And in this case, if the cost, what we are comparing, if the cost added with these modules of sorting and mechanochemical conditioning could be interesting from that point of view to have a cost which can enter after that in the market to sell these PVB recycled products. So in this case, we make some extrapolation, of course, because we are working now with prototypes, but if we go to higher scales in terms of sorting, in terms of mechanical processing of the laminated glass and chemical, we obtain a cost value of 758 euros per ton of recycled PVB flake that we could produce. And then to this cost, we will need to add the cost of processing to pellets, which is the data we are considering now in this final part of the project, and to processing in different applications. So here, okay, if we go to the prices, okay, comparing with the market prices, we have, okay, we compare with PVB flakes, we are more or less in the range because our cost is 758. Current prices in the market for flakes are 1,000 euros per ton, so we can be in the market. And although it's not included here, in terms of when we go to the processing of film, this has been calculated now. First numbers indicate that it depends a lot in the quantity of the mixtures of virgin with recycled material we are going to use, and also depending on this cost of this virgin material. The issue is that we here don't count with the cost values of this virgin material because we don't have these values. We have the market prices of this film, but it could be a space in the mixture and with the addition of virgin to have a material which can be which can be within economics. The issue is that we have also to test that these films with mixtures can be produced in similar conditions that current manufacturers do it, and to check which are the real optical values obtained when they make in their real conditions, because this can improve in some aspects the final quality. And okay, that's all about the results. This is just a slide about the consortium of the project. We are 19 partners in this project, from the research to the development and applications, including
But may
companies.
I suggest, Angelica, that we leave it here because we are running out of time. So I
Okay.
think we have the partners here. We can consult them on the website if need be. Thank you very much for presenting the Sunrise project and the state of affairs. I think that based upon your presentation, we see that a lot of work has been done, but that there also still remain some challenges open. And that, I would say, leads us to the second presentation given by an independent expert, Erdal Harmanchi, who will speak to us about the current PVB recycling challenges and knowledge needs for laminated glass applications. Erdal has over 20 years of experience working in different chemical and advanced material companies, and over 11 years of PVB-related experience. So, Erdal, if you're here, good afternoon.
Yes, good afternoon.
Welcome, and you have the floor for your presentation.
Thank you very much. Let me get it on the screen. Hopefully it will come through. Do you see my screen if I go into this mode?
Yes.
Perfect. Thank you very much for the introduction. Good afternoon, everyone. So I have put a slide deck together for us this afternoon, maybe giving you a little bit of a spin on the topic of recycled PVB. And the main purpose for me over the last 2 years has been, how do I get the PVB, which is going to be recycled, back into its niche application or common application. And in my case, this is about laminated glass with all its requirements so we can get to an A-grade material. I will cover quickly the drivers, of course, many of you will know, but also discuss a little bit about the value of the PVB in the standard commercial laminated glazing industry, the challenges which are still remaining, and of course have insights on the expectations of the end customer, typically the PVB producers and its laminators, and then anything about the closing message or things. As an introduction, let me tell you that what everyone is doing this afternoon, and all the companies and the brains thinking about to recycle PVB, it all fits in commercial activities on the planet, right? CO2 is a real thing, and money is being spent. And yes, this is not related to the car industry in specific, but if you read the last reports, many German OEMs, car manufacturers, are spending a lot of money buying CO2 credits. This is, I think, in my opinion, going to happen also about materials and raw materials. Everyone knows that European carbon cost taxation is on the way coming. I had a couple of discussions in the past months with industry leaders, players. Most likely what will happen is that the cost of this taxation will be distributed in the chain. One thing that is known that automakers are really good in doing is pushing the high cost, which is coming from taxation and all that stuff, into the supply chain. So I think for the big players today who are making the PVB, but also the recyclers of PVB on the other hand. There's excitement period and years coming to make sure that we can capture on the value by recycling the material and avoid additional cost and taxation to anyone in the chain. Why are we interested in recycled PVB? It has to do with the lower carbon footprint, right? If you compare today the virgin PVB sheet for laminated glass versus a recycled PVB, whatever technique that you are using, mechanical, chemical, or the combination hybrid of it, there's an estimation that about 20% of carbon footprint is still in the recycled PVB stream, but there's a saving of 80% compared to the virgin. That's the main driver where everyone on the planet is interested on how do you recycle PVB back to its normal applications. The challenge and the biggest challenge, also hearing from the previous presenter, remains the purity which is required for laminated glazing industry. And because of this issue of purity, I do believe that today what happens is mainly downcycling. So we are losing a lot of value of the recycled product, and we add it or we use it for low quality applications. These are tiles, carpets, paints, release foils, I heard sound installations, and all that stuff. It's a good start, but it's it's a long way to go. The market value of PVB today, 1 kilogram is about €4. And I have been excluding all the peaks and down things that the last 2 years have done. The prices are getting pretty stable. And today, in the best cases that I have seen in the market, by the cleaning actions which are being done, mechanical, chemical, hybrid models, in best cases, you can sell for €1 per kilogram in the market. So all that's to say that with everything which has been done to date, there's about 75% of value kill of the intrinsic economical value of the virgin PVB, which we can get out of the laminated glazing. On the other side also, if you want to capture this value, this €4 per kilogram, you have to deliver a quality that fits the needs of its main application, which is laminated glazing. That's where you need to go. So whatever we are doing, it's all good that we are looking for adjacent applications, but if you really want to capture the full potential and the value of this product, you have to focus on laminated glazing, and that's also where the biggest volumes are sitting for eating up all the pile of PVB, which is not being recycled still today. The challenges, I'm sure that is nothing new to the audience. The PVB, it has a strong adhesion to the glass. So we need to find a way to release it from the glass. Today, the typical thing which is being used is the mechanical. The contamination which is remaining after first pass, typically around 5%, needs to be removed in combination with chemicals, tensides, and water. The other side, when you are doing this process, you cannot go too extreme in settings and temperatures and harsh chemicals, because you will be starting degrading the material. And in doing all this, we also, of course, want to keep this process very economical, meaning that we still can deliver a product which has eaten up some of the value by going through the process, but it's not adding too much of cost to the product itself. From the last 2 years, I have been testing and investigating about 18 types of PVB, recycled PVB in a format. The slide on the left side, I will not go through detail. These are typical phases that you see in a cleaning cycle or a recycling cycle. The best that I have seen in the market, which is about 6 months ago now, has a glass contamination levels of less than 0.5%. That's the best that we are setting. If I compare this to what a typical PVB maker needs and requires, besides the percentage, which is still too high, is also the size an issue. Anything which is above 50, 75 micron typically results in extrusion issues, quality issues, non-usable products. And even on the next steps, any contaminant, which is in a multi-layer applications, can result in edge bubbles, all that stuff, which is a typical defects that you see in laminated glazing. So the contamination levels getting down, absolutely the right thing to do. Get below this 0.5%, focus on reducing the amount of particles which are still left there, how, to get it even less. But the mechanical part or the glass part is not is only one part of the story. It's an important one. It's only one thing. The recycled PVB exists on different elements, right? You have the resin, you have the plasticizer, you have the stabilizers and additives like antioxidants. And I think that the recycling industry needs to understand that you are selling a chemical formulation to your customer. You need to understand better what are you selling, what is the composition that you are selling, and how we are going to repeat it from every recycling batch to every recycling batch, so your customers are getting a consistent quality so they can adapt their process to it. I have put here as an inspiration a couple of very typical requirements from the PVB world, laminated glazing. Yellow index, very important. Understand what yellow index is, how we are increasing, decreasing it. Contamination levels, understand how much particles that you are still allowing in your material. Anything above 75 micron is mentioning birth, as it's critical to mention it as a part of the quality of your material. The haze, very important. Understand how we are changing, controlling the haze perspective of it, but of course also the physical properties like flow. This is the input, I think, that the recycling industry needs to give to their customers who can use it later on in their process. And they need to do adjustments to the adhesion, the roughness, the antioxidant, and the UV package, and also the plasticizer. The more consistent the input is, the better the process can be adapted, and the more successful the recycling or the recycled product can come out of it. That's what I think. So all that said, I think today a lot of us is focused on cleanness, which is still required to do so. On the same time, there is definitely a clear ask for broadening the standard of what is the quality of recycled PVB, which is being delivered or put back into the market, especially aligning with the end consumers and their applications. This is a eye chart, maybe in the room. It's a very similar specification that you can today Google and get on a PVB sheet version. This is what your customers are communicating into the market. There's much more of it, because this is the minimum and the basic thing that I think the recycled PVB should have as a specification when you sell it or when you bring it to your customer. It just gives an insight of that you understand the product, that you understand the ins and outs, and you start speaking the same language as your potential customer and the industry. To summarize, I think the important message from my side is the cleanness of the of the PVB remains the foundation. Drive it as low as possible. Focus on the size distribution of these contaminations, which is important in the final applications because it can cause significant defects and make the product not useful. Have specifications. Put a specification together to drive consistent batch over batch recycled material to our customers so they can set up their process. Make sure that we focus on positioning the product to the real end markets, right? That we capture the value and it's not a downcycling, but it becomes a upcycling process so we can be an alternative, a reliable alternative for the virgin PVB. Not replacing the virgin PVB, but at least going from today's typical 25% recycling in the sheet, going to maybe 70-75% of recycling, been a good alternative source to it. And I think, in my humble opinion, over the last 2 years, speaking with different players, the today's processes that we are using, mechanical / some level of chemical, they're going to be all needed to work together and collaborate together to show to the industry of PVB makers and laminated glazing that recycled PVB can really be an alternative for them. Very short, hopefully it comes in as I was imagining how this presentation could come. But in my time, so my name is Ardal Harmansi. I have been working in the PVB world. If you want to reach out after the meeting or have any comments about what I said, you're welcome to do so.
Thank you very much, Erdal, for this interesting presentation. This leads us to the next presentation by Claudia Labs. Claudia Labs is working at DIN, German Institute for Standardization. And Claudia is also participating in the Sunrise project. And in the framework of the Sunrise project, we have also been working on a SEN workshop agreement on RPVB characterization. And that is what Claudia will present us now. Claudia, good afternoon. You have the floor.
Good afternoon. Thank you, Olivier. So you can see my presentation now correctly?
Yes.
Sorry. Okay. Well, good afternoon, everyone. So yes, I will present shortly on the SEN workshop agreement regarding the RPVB characterization, which we initiated within the Sunrise project. So yeah, you have my introduction, which was kindly given by Olivier already. So I will shortly present you, oops, sorry, there. The first bit, the standardization basics, giving you some information also on the standardization organizations and what type of deliverables I usually elaborated. And then I will focus on the draft SEN workshop agreement on the RPVB characterization, which we have drafted so far, and will end with a short summary and outlook. So what is a standard? What is standardization? A standard is a consensus-based document that is approved by a recognized body on European level, for example, the SEN, the European Standardization Committee. And a standard provides rules, guidelines, and characteristics for activities and their results. It's based on consolidated results of science, technology, and experience, and it shows the state of the art for the specific topic. And by doing this, the standardization promotes knowledge and technology transfer from research to market and also within different markets. And it helps innovative know-how to be widely known and used. And during that standardization, all relevant actors are networking together to find the best solution and a consensus. So the principles governing standardization work are, first of all, the involvement of all stakeholders so that we really find a consensus-based solution which reflects the state of the art and which is coherent with already existing standards. And the applicability of those standards is, first of all, voluntary and also working within the standardization field and helping drafting standards is voluntary. And the public is involved at the inquiry stage, so when a draft is published. And unlike laws, standards are not legally binding unless they are stipulated in legislation or in contract, and then they become binding. What benefits do you have if you use standards and specifications, or if the general industry is using them? They usually enhance the safety of products. They promote the interoperability. They facilitate trade by diminishing trade barriers. They promote the common understanding, especially the standards on terminology and vocabulary. They support environmental sustainability, facilitate the uptake of innovation in the marketplace, and they reflect the outcome of research and development. And what kind of standardization organizations do we have? So there are standardization organizations on a national level. Each country has its own national standards organization. We have it on regional level, for example, at European level and at international level. And each of these organizations provides a platform for its stakeholders in a specific area for a topic to come together and to reach a consensus for that topic. They ensure that the system respects the World Trade Organization's principles of transparency, openness, coherence, and consensus. And they help the technical bodies in drafting their standardization and pre-standardization deliverables. And in most cases, they also are the ones who publish the standards once they're finished. At the European level, we have 3 standardization organizations. First of all, CEN, the European Committee for Standardization, which is basically responsible for all the standardization except for the topics which are being standardized by CENELEC and ETSI. And CENELEC is responsible for the electrotechnical standardization, and ETSI is responsible for the telecommunication standardization. So looking at the different standardization deliverables, on the x-axis we have the development time, and on the y-axis we have the rate of consensus. So if we have close groups of experts, for example, within a company, a corporate standard is usually quite quickly developed, and obviously the rate of consensus seen on an international worldwide view is not as high because it's only within the company. Then when you have open groups of experts, be it at national, European, or international level, you have different types of specifications. For example, the workshop agreement, which is the fastest, and it usually takes 10 to 12 months to be agreed on. Then you have technical reports, where you usually just have additional information being published, like data or explanations for a specific standard. And then you have technical specifications, which are basically from the content the same as the full standard, but either didn't reach the full consensus or were written in a very new field emerging from research. And then regarding the full standard, you have the different deliverables depending on which level you are, e.g. national, that would be, for example, the DIN standard, or in Italy, it's a standard from UNI. Then you have the regional standards. In Europe, it's EN, and the international standards from ISO, the International Standardization Organization. And so looking at the CEN deliverables more closely, there are those deliverables being developed in technical committees, where the experts who are working in those technical committees are being sent from their national committees to work on the European level. And here we have the European standards, and in short ENs, the technical specifications, the CEN-TS, technical reports, the CEN-TR. And then besides the technical committees, there are workshops where individual parties can directly join and are not necessarily sent by their national standardization organization. And these workshops draft CEN workshop agreements, shortly CEN-WA. And those CEN workshop agreements can be the basis for European or international standards at a later stage. So the concept for this workshop is that it's a very flexible working platform with lighter procedures than the procedures for the full standard, and direct and voluntary participation by the interested stakeholders, and those also decide on the working arrangements. It's open to any company, organization inside and also outside Europe, and it does include a public process. And as I already said, it's pretty fast with 10 to 12 months, with only few physical meetings and mostly being managed electronically and by web conferences. So what was the aim of the standardization activities within the Sunrise? We wanted to support the market players to use the RPVB in various applications, and the possibilities for research projects to actually perform standardization activities themselves is by launching a SEN workshop to draft a SEN workshop agreement. So as Angelika said earlier, in the Sunrise project, we investigated different applications for the RPVB, for safety glass used in buildings, road vehicles, or railway applications, for photovoltaic applications, peelable coatings, carpet production, and batteries. So if we want the RPVB to be usable for all of those applications, then obviously the RPVB must be able to meet these different requirements. So we decided to initiate a new SEN workshop, which was called RPVB, in order to be able to draft a SEN workshop agreement with the title Plastics, Recycled Plastics, Characterization of Polyvinyl Butyral Recyclates. And the kickoff meeting took place on the 12th of April this year in Germany. And in the draft SEN workshop agreement, we now defined the scope that the agreement defines a method of specifying delivery conditions for RPVB, that it gives the most important characteristics and associated test methods for assessing the RPVB, and it intends to support parties involved in the use of RPVB to agree on specifications for specific and generic applications. So let's take a look at the draft SEN workshop agreement in more detail. So the main information or biggest part of the SEN draft is the table we have in there with different characteristics of PVB recyclates. And those characteristics are divided into parts. A, the mandatory characteristics, which are required to characterize PVB recyclates in general and which are needed for all applications. And then the optional characteristics, which are needed to characterize PVB recyclates for specific applications or specific customer requests. In that table, we also have the associated test methods. And additionally, the SEN workshop agreement requires that each batch needs also the information which of the product name and of intended and suitable applications for this RPVB. So what are the mandatory PVB characteristics which we have included in that table? It's ash content in accordance to a specific EN ISO standard. Color, in this case only the visual inspection. Impurities, also based on a standard. Then the information on the original application, which obviously needs to be declared by the supplier. So for example, whether the PVB came out of windshields or out of building applications, and then also whether it's post-industrial or post-consumer, because that gives information about the possible degradation. Then the plasticizer content, the residual humidity, and the yellowness index. And then with regards to the optional characteristics, we have adhesion to glass, color again, but in this case, according to the EN ISO CIE 11664 Part 4 standard. The elasticity modulus, Vaxer modulus, filtration level, flowability, glass transition point, haze, light transmittance, melt mass flow rate, refractive index, tensile stress at yield, and tensile strain at break, and the thermal conductivity. And for example, if you now would like to use the RPVB for laminated glass applications, the workshop participants agreed that you would, in addition to the mandatory characteristics, also need to use the characteristics for color, glass transition point, haze, and light transmittance for a potential buyer of the RPVB to have enough information whether it has a quality which can be used for the laminated glass application. So right now the STEN workshop agreement is a draft, where we just finished the 30 days public commenting period, which was in October. And we will meet at the end of this month to resolve all the comments which we received on the draft and to finalize the document so that it can be published end of this year or beginning of next year. And will then, once it is published, also submit it to a technical committee, in this case, CENTITI TC 249 and its working group 11, plastics recycling, so that it can be transformed into a CENTIS or a European standard in the coming years. Usually it is so that CWAs have only a short lifetime. It's first applicable for 3 years, and then the workshop participants can decide to confirm it for another 3 years, or to revise it, or to withdraw it. It has to be withdrawn or to be transformed into another deliverable after 6 years. And if a TC decides to transform it earlier, that is possible. And we hope that this will be the case for this CEN workshop agreement, so that it can be used widely within the industry. And in order to help the process, we had a liaison with CENTITI 249 and its working group 11, plastics recycling. And they have, for example, published a standard series on recycled plastics for various plastic types, just like we have now done with the PVB for the characterization of the recyclate. So in summary, the aim of the CEN workshop is to promote and facilitate the use of the PVB recyclates. We hope to help with this by defining mandatory and optional characteristics of the RPVB in the workshop agreement, and that the workshop agreement can be used by the interested parties to agree on the RPVB specifications. And once it is published, so hopefully beginning 2025 at the latest, you can actually download it for free from the website you can see here. And then we'll see if it can be converted into a European standard within the next 3 to 6 years. Thank you very much.
Thank you, Claudia. Are there any questions until now to the presenters that already made the presentation? No? Okay, then we go to the last presentation before well-deserved coffee and comfort break. We have here next to me, I have Ivano Menzo from Industriali Minerali, who will give a presentation about the role of his company within the Sunrise project. Ivano, you have the floor.
Thank you, Olivier. So what I'm going to tell you is why Minerali partnered this project and the role we have in the project, and why we can benefit from a successful end of this project as well. So, as already introduced, I'm representing here Minerali. It is a mining company. Owned by two Italian families and one German company that employs around 600 people with a turnover of 200 million in 2023. And in the Sunrise project, we have a specific role that is the one at the beginning of the process. As you can see, or as you can remember probably from the presentation that Angelica made, we were the one supplying the laminated glass waste to this MECO that is making the test right now. And the goal is then to test the machine in real, I would say, in the real environment, facing the issue that we have to face every day while we have to deal with laminated glass and PVBs as a waste. If you remember back what Angelica said in the beginning, what is the outcome of this process is glass powder and recycled PVB. So what the added value product is the recycled PVB, while the waste of the process is glass powder. What we do in our company is exactly the opposite. So working for us in the Sunrise project is exactly shifting 180 degrees the paradigm we work with every day, because we recycle laminated glass to get glass powder, simplifying the process, while we have to dispose of recycled PVB. And every day we receive this kind of waste from the market, and we have to deal with also not only the glass coming from laminated glass and windscreen, for example, but also glass coming from bottles. And as you can see from this picture, what we receive is not exactly this kind of glass pieces, but a mixture of different kind of glass coming from laminated glass, windscreens, bottles, containing a lot of other impurities and pollutants like metallic pieces, plastics, paper, PVBs as well, and so on. So our process is quite efficient, as I'm going to show you in a minute. But the less we get impurities in there, the better the process will be at the end. This is pretty straightforward to be understood. So in Minerali, we have fully devoted a plant in the northwest part of Italy, in a specific company called Sasil. This is the plant, and I'm briefly going to share with you what we do in this plant. This plant was built in the mid-70s to treat mining products. So once the quarries was exhausted, we started working on wastes, and more specifically glass wastes. So what you see here is an example of conversion of an existing plant into something that only deals with circular economy. I would say from 70 to 80% of the products are circular economy products. So we receive the product from the external collectors in these warehouses, and then through proprietary dry and melt processes, we transform the waste we get into, again, valuable product, mainly glass that is turned back into the glass industry processes. What you see here are the processing waste, processing water treatment lagoons. And to go back to one of the questions that I got from Olivier at the beginning of the presentation, PVB for us is a waste. So we deal it with within the fine particles from the wet and of course the dry processes. And we have to deal with as well while we treat the processed water. So the less we get as the input, the better for the process in itself. So to explain you what we do in Sasil, I'm going to use these pretty straightforward schematics. So imagine 100% of input material in weight that we get from the glass bins that we have in every cities. So this 100% is then treated in primary recyclers, where they are usually able to cycle back 75% of the glass scraps coming in. In the past, the other 25% was not treated as well. We were the first one dealing with this kind of primary recycling waste in Italy as well. So of this 25%, we divided into 5% that can be recovered immediately because it is something that it is easily separated from glass, like aluminium and metallic pieces that can be easily picked up from the primary recyclers, while the other 20% waste goes into our plant. And as you can see from these schematics, of this 20%, we are able to add value to 19% and landfill back and dispose of just 1%. In this 1%, we have PVBs as well. So with our proprietary processes, wet and dry, as I was saying, we are able to then divide based on granulometry and based on the application 3 different final destination of the input material. So the powder mainly goes into the brick and cement technologies, and in the fines is where we find the majority of the PVB. 3% is then transformed into something that can be used in insulation and construction and ceramics. This is as well a very nice application that can be used in building as well, while the majority in weight of the input goes into the glass industry as well. We are working to reduce this 1%, and a key leverage of this is receiving less PVBs in the laminated glass. And thanks to this project, we hope having this process ready. An added value of this project as well is also, as we have optical sorting in our factory, the sensors and the, I would say, the technology, the digital technologies that we have developed could be applied as well in the process. So we are really waiting for the results to come and applying them from an industrial perspective.
Okay. Thank you very much, Ivano. Are there any questions for Ivano? Everything clear? Okay, great, wonderful. I would say it's time for a break. After the break, we will have a look at PVB recycling from different angles. We will look at it from the perspective of a PVB producer, because this perspective is different from the one of a glass recycler. So following the presentation of Tobias, we will also have a look at management practices for glass recyclers who get windshields. I think that's also important. And we will end our workshop with a look outside of the European continent, where we will look on how they treat PVB in India. So I propose a break now until 4 p.m. Take some time to have a good coffee. If you have any questions, you can come by and see me or see Ivano or the speakers who are here. See you back at 4 p.m. Welcome again for the second part of this workshop on PVB. So as I said just before the break, we will now look at PVB recycling from different angles. And the first angle we will look at it will be from the point of view of a PVB producer. And we are very lucky today to have Tobias Techstein here from Kuraray Europe, Kurarai, which is one of the big PVB producers, producing companies. And Tobias will give a presentation about the vision of Kurarai on PVB recycling. Tobias is Sustainability Manager at Kurarai Europe. Tobias, you have the floor.
Yeah. Thank you for this kind introduction, and yeah, I'm happy that I'm here. It's my first visit of the ECOMONDO here in Italy, and also my first visit here, so I'm really happy to be here. So let's jump in. I heard a lot of fantastic things in this workshop already, knowledge about PVB and also ways to recycle PVB and in end-of-life usage. So at the beginning, oh, this is not working. It's on, it should be on.
Try to aim the computer. Yeah.
No, it's function. Okay, let's go. Yeah, my position is the Sustainability Manager in the Kurarai. And the Kurarai is a global operating company which producing a lot of chemical goods from the functional units of vinyl acetate monomer, isoprene chemicals, fiber and textiles, and functional materials. And I specifically work for the AIS, this is the Advanced Interlayer Solution Divisions, and we're primarily producing PVB films out of PVB resin. So let's jump in. We are a global acting company. We have big production facilities here in Europe, in America, and also in Asia Pacific. Our R&D labs are located directly in Germany. Feel free to contact us if you need any background information or anything else. And we have everywhere sales office. So, wrong direction. So, PVB. I start with a general introduction. What is PVB? It's called polyvinyl butyrial, and it's coming from a vinyl acetate functionality, a vinyl alcohol functionality, and basically a butyrial unit. And when you put these three together, you get a tear polymer in the end, and this has the unique functionalities what we use in the laminated glass safety application. The production here is basically a scheme of our production process. No worries, this is everywhere public. You can look it up, Google us, and you will find it. And it's no secret that we use PVB resin. We add here plasticizer. I heard this already in this talk a lot of times, so there is knowledge about it. And we add some additives. The additives, of course, are secrets. And if we want to produce a specific PVB film, we will change the additives in it. Thereby, we will make also a different PVB type. And this here is also important knowledge about it, that there are several PVB types in the market. And if we want to recycle end-of-life material or even other materials, it is important to sort it out at the beginning, because only then we can achieve a recycled PVB in high qualities. And we mix it, we extrude it, then we have a relaxing zone where the stress is getting out of the material, it's cooled down. And at the end, if you want a PE interleave in it or not, you get it also in cooled. Maybe you visit once a recycling place, and when you put PVB together, you will get a big chunk of material which will stick together. This is our solution. This is also in the market. You put a PE interlayer in it that the PVB cannot stick to each other. Second option would be to cool it down. The lamination process is also here depicted. For laminated safety glass, you take 2 piles of glass, the PVB, put it together, and in the end you get the laminated safety glass. The real picture of it is such a lamination line here, and it starts with washing the surface of the glass. Then you pile up everything together, and then you run it through the nip rollers. They're applying pressure at the end of the glass, attaching it together. Then it's running through an oven, and the rest air which is inside of the laminated safety glass is dissolved in this process, and thereby you're creating a clear compound. So In the end, we use, of course, or our customers use the laminated safety glass in architectural applications, also in the automotive industry. And just recently, we also introduced our new interlayer solution for sustainable glazing. I will give, in the end, a little bit more details into this process. So we, as the RES, see sustainability as an opportunity. Why? Because we're following the ESG rules, and thereby we want to protect the environment, also the social aspects on the government's aspects. And we want to develop with partners or by ourselves new ways or new technologies and new products which are lowering our carbon footprint to reach our global emissions reduction. So our mission is to develop new technologies, to entering new fields for developing new products. We, as a QRA, now I'm speaking globally, want to reduce our Scope 1 and Scope 2 reductions by 30% up to 2030, and we want to become net zero at 2050. We currently don't have the Scope 3 emissions, but they are under revision. They will soon publish. And we, as the RES, have a more ambitious goal. This means we want to reduce our carbon footprint, or the basic carbon footprint, our Scope 1 and Scope 2 emissions by 75%. We also want to become net zero in 2050. And I spoke now a little time about Scope 1, 2, and 3 emissions. I don't know if you ever heard about it. It's basically a separation of each emission class into Scope 1, 2, and 3. Scope 1 means direct emissions on your production plant. So if we burn fossils to produce electricity, we do it on our plants, and thereby we produce carbon dioxide emissions. When we go now to Scope 2 emissions, it's also electricity, but this electricity is produced, for example, on the different plant. For example, when we generate electricity from coal, this is not generated in our production facilities, it's done somewhere else. And here's also an interesting part that we cannot influence, basically, this emission class. So we only can influence it when we purchase green electricity. And thereby we can reduce our Scope 1 and 2 emissions. And the most interesting thing and also complicated emission class are the Scope 3 emissions. For our compounds, chemicals, we need to purchase our starting materials from our suppliers. So we are also directly connected to their carbon footprint they are selling to us. So if we want to reduce our Scope 3 emissions, we have to get in contact to them, talk with them, and also evaluate maybe also the quality of the product in respect to the carbon footprint. Because only when our suppliers also working on reducing the carbon footprint, it's possible for us to reduce our Scope 3 emissions. So this is also classified as indirect. This is a summary of what we're standing for. This can be seen at our sustainability report. You can also Google it, then you will find it. And in numbers speaking, we want to reduce our carbon dioxide emissions from 120 kilotons to 30 kilotons of CO2. This is the 75% reduction. And the more interesting part is, where are we on our roadmap? So only Scope 1 and Scope 2 emissions. On the baseline is 2019 up to 2030 with these 30 kilotons of CO2. We are here at 120 kilotons, and 2023 we are ahead of our schedule and have also currently a little bit more room to breathe until the next steps coming 2024. This will coming soon, 25 and so on. And the next steps will be the most difficult ones. So looking into the future, how can we achieve our global carbon dioxide reduction? As I said, we can change to renewable electricity, so we can change our energy purchase. We can also increase the yields of our reduction. This is quite simple. or not quite simple, but it's a way to look through, and also energy recycling. This means looking into heat pump systems and so on, also in the industrial way. For our recycling business, we can look, or basically our chemicals, we can look into our suppliers and also their carbon footprint, basically, and choose between each other. And one more interesting part, and this is also connected to the Sunrise project, is the increasing of recycling. And we spoke also today a lot about recycling of PVB, and we are really highly interested in this topic, also really to gain the PVB in a circular economy. So currently it's landfilled or burned, it's sad, it's a material with high energy, basically, and a high value. So it would be good when we would develop in the future such a raw material source for our company. And the next thing is, but this is more looking into the future and will also need more work, is mass balancing. I only will quickly come to it. Here on this flow diagram, you see basically how PVP is generally produced. In the end, we have our plastic, and the idea of a depolymerization or chemical recycling is that the recycled PVB is transferred back in the chemical production and can be used here. Or going back to bio-naphtha, which is then processed into basically in other chemicals. This is the idea. We have to go, but it's a short story. And for this, basically, we need mass balancing. Mass balanced products some of them are in the market, but we need the acceptance of our customers to push in this direction. We certify we think that the certification with the ICC Plus institution helps us a lot, but the problem is we cannot build a green production facility. This is the production site in Frankfurt Höchst. We would need another production facility in Frankfurt for only producing green chemicals or biochemicals, and this is not possible. We cannot invest so much money in production of a new facility. But this is an interesting topic, but not today. So we have also then looked into mechanical recycling to polymer recycling. Sunrise project has also made a good effort in characterizing such compounds and also finding a way to get the PVB out. And so where are we currently? So the laminated safety glass is recycled by glass recyclers in Europe. It's a raw material source which is declared as waste. That's sad. And only 9% of post-consumer PVB waste is recycled. We want to increase, of course, this ratio and not downcycle it maybe into glue or other compounds. We want to recycle it back into the plastic production. And what is important in our perspective is that we directly sort from the beginning of this process the clear product, the acoustic product, and the tinted product. So we have, for example, a brilliant black. This is a black PVB. We have a white PVB, and we have clear PVB. And then there's the acoustic PVB. This is also clear, but there is a higher plasticizer content in it. And if you want to produce a PVB for a clear product, you can only recycle clear PVB. When you mix acoustic in it, we cannot use it. So pre-sorting is essential. And also maybe this enable us in the future maybe to generate several waste streams for each PVB type. And for example, it's also important that the dismantling of the laminated safety glass is done in a clean environment. I visit once a glass recycler here in Europe. I know that it's sometimes not so easy to make a clean environment, but there are also ways where a big cleanliness is needed or required in the process, and where cleanliness can be not taken into account. But that's all details we have maybe to discuss and get also in the discussion about it. And we as a PVB producing company see that the ash content is extremely important for us. When we have a lot of residues, glass or inorganic materials inside of our PVB, it's nearly impossible to produce it or to use it as a raw material source. We also heard about technical issues with the extruder, and there is also details. And also we have to characterize the recycled PVB in a laminate with a light transmittance above 87%. And of course, when we want to reduce, when we want to recycle clear products, this color has to be transparent. I know also for glass recycling companies, this would be also a huge effort to buy a laminating process line. So what we can offer is that when you have PVB, recycled PVB material, you can send it to us, we will characterize it and give it a benchmark. Also for glass recyclers in Europe, where are we, where we have to go, and what maybe are the next step that we're getting here also in the discussion in characterizing these compounds. So, and as a short outlook, I want to highlight our newest products. We made a new sustainable glazing solution. It's called Trosivol R3. R3 stands for reduce, reuse, and recycle. And what you can do is basically, we heard once that PVB have a carbon footprint of roughly 5. Global average. We can reduce the carbon footprint almost by 50% when we use post-industrial pre-consumer waste. So we have currently the technology to use it and also to feed it into our products. And the next project basically is the Class A. This is where I'm currently leading, or this is one of my duties at the QRI currently. We also managed to develop a product with cutting-edge technology, which enabling us a usage of 100% recycled material. And thereby, you can create products which have an extremely low carbon footprint of basically 0.2. So this is where we are, and this is where we also want to be. And yeah, so we cannot create the future alone, and thank you for your kind attention.
Thank you, Tobias. Are there any questions or any comments on the presentation of Tobias? I noted that a pre-sorting of acoustic PVB is also needed.
Yes.
Is it possible to explain that a little bit more? Why?
So when you have acoustic products, you have a higher plasticizer content. And when you mix it with clear products, which have a lower plasticizer content, there are some mixing effects in it, which will come later in the laminate. So you see the error of mixing this indirectly in the laminate, and there it's too late. So therefore, the sorting of the two products is essential. But also one of the Sunrise, project was also to build a near-infrared detection system or Raman system to sort these kind of materials. And in our perspective, it's really important to get this effect out of our recycling stream.
So if I understand correctly, you're mainly focusing on the clear PVB, not tinted, not the plasticized, but the clear one.
I mean, like the clean or the acoustic products are, from volume speaking, the biggest markets. The tinted products, or I mean like shining white, translucent white, and brilliant black are also good in sales, but the market is not so big. And if we want to achieve a good recycling system, it would be good to start with the lower hanging fruit, and this would be the clear market.
Yeah.
And when we build together a recycling stream for such clear systems, we can get the knowledge about what we have to do and then transfer it to the next category, and this would be the acoustic products. And when we transfer such a system on acoustic products, then let's go further. And also in respect of end-of-life recycling, I think starting with end-of-life recycling now is not the right way to go. We have to learn first with virgin material. Where are we? Where is our benchmark? Start with the lower hanging fruits. And when we can do it with virgin material, then go to the next lower hanging fruit. And then in the end, go to end of life recycling. I think this is a process which is better for a cooperation between glass recyclers and the PVB business.
But on what or which flows are you then referring to? Because the majority is end of life. So to what? Yeah. So to what flows are you referring to? Because the majority is end of life.
Yes, I can I have my presentation?
If we have time, I don't want to steal too much time from the other speakers.
No, we are fine.
Okay.
We are fine.
I can
Good.
show it to you, or maybe I can also tell it you. So when you are a glass laminator, you take one sheet of glass, you put a PVB on it, and then you put the next glass on it. You put it through an oven, and then in the end, you get a big laminated safety glass out of it. But this glass is then cutted.
Yeah.
So you produce a cutoff. And this cutoff is post-industrial, pre-consumer waste. It has a really good quality. So if you want to maybe start a recycling business, this would be the waste types which we have to consider. And also from materials, because we have also to consider there are also competitors on the market, and mixing competitor materials with our materials is sometimes a little bit difficult, but we have the knowledge to who we are selling it and who is producing our cutoffs. And this might be the first entry into the recycling.
Clear, thanks.
See, Ivano has also a question, a comment.
No, I was just like to comment to your last point, Tobias. I can give you a parallel to what we are doing in the ceramic industry. So if you think about big slabs made out of ceramics or e-stones, they have the same problem. While they cut the final shape, they have like waste. And we worked in the past to develop technologies to help them to recycle immediately from the line that kind of waste. I see potential issues in what you are doing with laminated glass because the process is slightly more complex, but there are parallels, and you find a lot of literature as well on this about, let's say, ceramic industry, not glass industry. But I see similarities in what you were describing.
Yeah, cool. Yeah, also I think so the technology or also the characterization of recycled PVB is there. And when you look into Europe, there are also promising PVB recycling ideas, and also companies were working on it. So the quality is there, and also the knowledge about this process. We have to get this running. This is the only issue. So yeah. Therefore, I'm here, looking for a connection.
Thank you.
Okay, thank you very, very, very much, Tobias. Sorry. So this brings us to the next speaker on our event. We had a look at PVB recycling from the PVB producing side. Now we will look at it from a glass recycling side. So, as you pointed out, Tobias, there are a number of things we can do as glass recyclers. And one of them you mentioned was a pre-sort, but also maybe create different waste streams and ensure a clean environment. As some of you may know, the reality on the terrain is a little bit different because the glass recycling is a totally different business, more based on volumes and than it is maybe on very specific and complex processes that of dismantling. So also from a glass recycling perspective, we would need to do a number of things in order to ensure that PVB can be recycled in the future. And for that, I would like to present Baudouin Ska, Vice President of Verver, who has been working on on guidelines, on management practices in the framework of the Sunrise project. So good management practices for glass recyclers. Baudouin, you have the floor.
Thank you, Olivier. So it will be maybe a summary of what we got from information from Loredera, Angelica, also from Claudia, and Erdal, to see what are now our members facing with the situation. So the situation today is this one. You see a storage of laminated glass damaged. You see the way how it is handled and transported. And then you hear from the colleagues of Kurarai, you have to select the PVB type, the plasticizers, and the cleanness, and so on and so on. So how can we manage it? Because today, the glass recyclers are doing their job is to recycle glass. And when they get laminated glass, they have to get the PVB film out of the glass with as less glass as possible in the PVB, and of course, as less PVB possible in the glass. Because if you bring PVB in the glass furnace, you will have an incineration of the PVB with production of fruit, and you will get black glass and not transparent glass. And on the same, on the other side, if you get glass in the PVB, if you do an extrusion, you can imagine the damage you get on your machine, which cost thousands of euro, one use, and you can forget it. So that's the situation today. What could be the situation? What we do, of course, efficient selective of the two fractions. And the best way today, the cheapest and easiest way, is to expose the laminated glass outside to the effect of moisture, dust, temperature, and UV. And then you get a physical separation of the fractions. You get it in a shredder, and you get the two fractions with a suction or pressure system. But then you get a PVB fraction which can certainly not be used to produce in a closed loop new PVB film. The situation tomorrow is to get, as you see on the right, would be perfect to get laminated glass piece by piece with a stamp on it, coming from Kurarai or a competitor of Kurarai, produced in 1978 from a company Mercedes, and so on and so on. Forget it today, but maybe tomorrow could be possible, thanks to the multi-sensor developed by Sunrise or a new possible system. At least we can start step by step to go in this direction by keeping the material dry as from the beginning until the processing. Avoid direct exposure to UV light. You see in your windshield you have a range which is black to avoid penetration of UV during the use of a car. That's the reason why it is black. Preserve also from external contamination, of course, dust, other material, waste, and so on and so on. Now, depending on the final recycling destination and process, of course, you need a further glass extraction if you work on a dry process, or not if you go in a liquid phase by extraction in a solvent, then it is not so mandatory to have as less glass as possible. For the PVB point of view, for the glass point of view, of course, you lose material. Avoid additional of chemicals, because in the processing, it is sometimes, we'll see it, easy to avoid calcium carbonate, to avoid the glue property of PVB. But that's a poison in the process. So please, that's a message we got from the users of PVB, don't add chemicals to it. Try to solve your pre-processing by keeping the material as clean as possible. And you can then reprocess the flakes produced by the first separation step in pellets to have other uses. A very important step is also, as I explained earlier, the traceability. The origin of laminated glass, is it coming from construction or from construction, renovation, demolition, or age. Or automotive, the brand, age, acoustic, non-acoustic. For example, Tesla was criticized at the beginning for the poor acoustic insulation. Now they decided to equip all their cars with only acoustic laminated glass. Not only the windshield, also the rear windows and the roof. So that means if we get as glass recyclers Tesla glass from 5 years ago, it's not the same quality as the Tesla glass from today. Will we be able to stamp each piece of glass we will get from a dismantling company or from an end-of-life vehicle dismantling company? That's a question. In storage, of course, they say also keep the material as clean as possible, so don't send it in bulk as we saw with the bulldozer. Place it in big bags under a roof, storage in a dry system. The storage time also, if you get the PVB alone, you will get an effect of coagulation or agglutination. So instead of having flakes, you will get a block of 1 cubic meter. What can you do with it when you deliver to Kurai? They will say storage, landfill, of course. The moisture is also affecting the adherence of the pieces, sorry. Light protection and, of course, clean environment. And the properties, as we saw in several presentations also, the color is very important. The light transmittance to remain transparent as far as possible. The moisture reduced below 1%, and the ash content also reduced below 1%. Now we have spoken until now with, let's say, the high quality, the closed loop, the dream we have. Of course, today there are other applications used, what we call the lower quality applications in open loop. You have then, as presented in the presentation of Claudia, a peeling layer which is produced via a first dispersion solution. You apply it on, let's say, a piece of material you have to protect during storage or transport. And when it's delivered to the client, protected, just have to remove this layer as a post-it of 3M, if you can imagine. That's one application. Another application is just to produce as pure as possible flakes. You have a well-known application in underlayer of carpets, with then no importance of the color, for example. You have textile application to give some properties of resistant to water and things like that. And as explained already also earlier, application in battery productions to have insulation between the metal parts of a battery. And you have the solar panels as well to replace the EVA material. In all these applications, it's based mainly on mechanical recycling. In the sector, let's say the classic recyclers are advocating for mechanical recycling instead of chemical recycling. Our opinion for PVB is that we should have to go more and more to chemical recycling, knowing that the pure chemical recycling is to depolymerize the polymer into monomers and to build again the stone. But in PVB, it's not possible. But the chemical recycling is to understood with PVB as being a solution in solvent to extract the PVB and only the PVB. Then you lose the impurities as dust, glass, and so on, but you lose also the plasticizers, which could be a solution for the acoustic PVB, I don't know, but you anyway have to re-add the plasticizer, which increase the cost. You get the lower material a material, let's say, cheap material. But if you have to add all these applications and all these additions, you get close to the price of virgin material. And how can you explain to the client that the virgin material comes in good competition with the recycled material? That's a question.
It's difficult when making such an extraction of a plasticizer from acoustic. You would end up with a material which has not a defined ratio of plasticizer in it when we buy it.
It will be hard to actually determine the amount of plasticizer in a compound. So it would be easier for us when we go the way of a combination of mechanical and chemical recycling and evaluate at the beginning this process. I think this mechanical and chemical recycling will be the major part of this whole recycling business. And in the end, for specific specialized compounds, we need specialized methods. But this might be in the future also a combination of other projects currently. So it's evaluated also in our side, and we have to see where we have to go.
Okay. So the requirements for open loop, of course, if you work with the solution and dispersion, you have a manageable residual content of glass, because in a solution you have a sedimentation of glass, so it's a good separation. But you need to stabilize the dispersion to have a minimum dry content. In the trials we did within the Sunrise project, we had some problems with that. It was not able to get a stable dispersion. You got also the sedimentation of the PVB. When you work with flakes, of course, you have to ensure the good conditions for storage to avoid the coagulation of the flakes. And as explained already, to avoid addition of anti-cohesion agents as calcium carbonate.
So but here it's not impossible for us.
So in respect to the flakes, for us it's not impossible to use it. When the flakes are basically have a low glass residue content in it, and this is verified, then it's no problem to put it into an octabin, let it scramble together, we get it, we use it. We can process flakes. This is, for us, no problem. But the glass has to be out of this material. Then it's no problem. When the glass is inside of the PVB still and it's getting chunky, then it's getting a lot of work. And basically the material is then lost. So the process has to be quite sharp to get the glass out. And then there's no problems with flakes or making a sticky mess.
Okay. Something which was not mentioned during all the presentation is that I think in the production of virgin material, you control the temperature always. It's a cooling system to avoid the increase of temperature. Also, the transport is in cool transport.
Depends. This was a little bit too loud. This depends on our customers. There are some customers who wants to get the compound with a P interleaf, and there are some customers who wants it as a refrigerated solutions. But in respect to the recycling of PVB, how we feed in the material into our new technology, we can process it as flakes. When the flakes have a really low ash content or glass residue, then we can process it. And it's not a problem to use a guillotine to cut it into pieces and then reuse it in our production facilities. But the quality has to be established. Only then we can use it.
Minimum quality standards, yeah.
Minimum, yeah.
Okay, then for the pellets, of course, as I said, the control of production of temperature, because if you increase the temperature, you will increase the color of the pellets. You can start from transparent flakes, and you will get yellow pellets.
We'll also get gray and black. So currently Tesla also doing a lot of acoustic products
which are tinted gray. And so Tesla, for example, is producing a lot of electric vehicles with gray products. When you have such a gray acoustic product at the end in your recycling machinery and you get this PVB out and you put it into a granulator, you will get gray PVB.
Gray PVB.
And this is the problem. So this has also to be sorted out. This cannot be recycled.
So you see, it's a technical challenge. It's also an economic challenge. Is the market, and I look again to the producer of virgin PVB, is the market of your clients prepared to buy recycled PVB or not? And I would compare it as a conclusion with the packaging of glass. Today, nobody asks how much does it cost to collect selectively packaging glass. In all the countries, I don't know from which country you are, but you have in all the countries today in Europe a selective collection of packaging glass. Nobody asks how much it costs. It is mandatory. For flat glass today, there is nothing. The only thing we have is 70% of recycling for construction waste, but you know, glass is a few percent if it's 1% of a building. So if you recycle glass or not, it doesn't matter. You can reach this percentage of recycling in the building. In automotive, we have today a directive which says that you have to do the maximum to recycle glass. That's just a wish, a good wish. Today, the Commission last year proposed a revision of this directive to make it more stringent and more mandatory by changing the type of rule from a directive to a regulation. That means applicable on the same way in each country as from the date of publication. And the Commission proposed a mandatory dismantling of the glass, which is the first time. In a car, you have roughly 3% of glass. The target for recycling are around 95%. So again, you do not need the 3% of glass to reach this target. But if it's include mandatory dismantling of glass, you will at least get the material for recycling, for the glass and maybe also for the PVB. If it's pre-dismantled, you would be more able to recognize the type of glass and the type of PVB in a material. Today, all is going in a shredder and you get pieces of glass. So, and what can you do with it? Just landfill it. It is so contaminated, even for the glass, that you cannot recycle it on a good way. You can make granulates for road constructions, but we do not consider it as recycling. Officially, in the counting of Europe, it's considered as recycling, but let's be serious, it's not recycling. And we see now the position, of course, the Commission proposed it. The Council has to pay, so the Council will reduce the targets. And the Parliament was more green and wants to boost it. But will the new Parliament be as green as the former one? You got in the title of the conference a question mark, and I think it's one of the question marks we remain with at the end of the conference. So thank you.
Thank you, Baudouin. Are there any further questions or comments on this topic for Baudouin or for Tobias? No? Okay, thank you very much. Then I think we can leave Europe and go to India and have a look on how in India we recycle and work with windshields and recycle PVB. So I have the honor to present you Mr. Anil Rati, who is the managing partner of Romani Innovation PVT Ltd or Lakshmi Polymers. Good evening. Good evening and welcome. Do you hear us?
Yeah, I can hear you. Can you hear me?
We can hear you. We're just adjusting the volume here of the of you speaking.
I don't know what I did.
It's okay.
It's okay, I think. So I will give you the floor to present your company and give your presentation. And thank you very much again for being available at this late hour.
Actually, just I am looking to find out the documents, how to share it, because it's quite new for me to do the presentation. So will it be fine for you if you give me a minute to just find my documents and just...
Otherwise, we can share your presentation, and if you say next slide, we will go to the next slide.
Just let me see if it goes.
It's working, I think.
It's working.
Opening.
Just give me a minute. Yeah.
Yeah. No. If you
Okay.
if you go a little bit to the right, one more. Yeah, there it is.
Okay.
Yes.
Yeah. Is this okay for everybody now?
Yes, perfect. Thank you.
Okay. So we started our career with the Lakshmi polymer, and everybody knows with the name of the Lakshmi polymer. So now the company is growing. So now we shifted to the private limited company, which is the Romani Innovation Private Limited. So Romani Innovation Private Limited and Lakshmi Polymer is the same company. And we are the company who's working for the windshield and the PVB recycling, and we're working to the circular economy. So now comes to the team. So currently we are the team of 75 people. So in the company, we have an executive director, Sharwan Sharma, my wife, another director, and I'm the managing director in the company. So usually I look after the technical part of the company. So if I just give them a brief history of the company, that we started this company in 2004 with the manufacturing of the EVA compound. So manufacturing for the EVA beach sandal. In the 2006, we started the beach sandals manufacturing. So, and by 2015, we start doing the PVB scrap recycling and compounding also. And in the 2017, we started manufacturing the car mats from the PVB scrap itself. It's just the brief history. So this is the windshield embedded glass. Everybody talked a lot on it, so there's no meaning to tell what's the big quantity we generate every year in all the world. So now it's come with the windshield recycling challenge. So you have to develop a technology, first of all, which should be economical, how much machine investment cost you do, what will be the running cost, how the quality you get, how the quality of PVB scrap get, and what will be the final usage. As we are in India, so definitely our manpower is quite cheap. So we develop the technology where we have not invested so much in the machine. Yes, our running cost is little bit higher due to the more manpower in that, but our machine investment is just nothing. Means like we develop them just for the PVB recycling part. We developed the machinery just in 50,000 euro. So you can consider how, like in India, so we have to see that part. So these are machines which are designed by myself. The first machine is there, so it's used for the crushing of the windshield. The next machines comes just for the separation of the glass and the PVB. About 95% glass we remove at the second process. The third process we have a grinder, so which again remove the whatever the glass is to the PVB. So we remove here, and now it's come the fourth machine is like high spinning machine. So here also we remove the remaining glass, and after that also if some glass is stick in a fine powder, then we wash it in this washing machine. So all these machines are designed by ourselves, and they all are available. We developed in just like 50,000 euro, and we have not get any guarantee from Indian government or anywhere. It's all done by our own. So this is our PVB compounding pelletizing line. So here it is the Banbury we use here, because in our process we mix some additives in the PVB to develop some compound. So it's come more easy and more good quality we get if we use the Banbury here to mix the PVB with the other additives. So then it's go to the extruder here where we have the screen where we take out if some contamination is there. Then it's go to the final extruder, we make the pellets there. This is our car foot mats manufacturing plant. This car foot mats again made with the PV scrap only. So what about the today's status? Right now we are recycling like 1,000 tons of the windshield because in India we don't have so many cars. So we are basically located in the north part of India near to Delhi. So in the northern part, in a circle of 500 kilometer, we cycle almost every windshield. So we have a compounding line with the two compounding lines, so with a capacity of like 200 tons per month. So mostly we sell this PV compound to the shoe manufacturer. And along with that, we are having an injection molding machine to make the car foot mats. That also made from the PV scraps. And we are having in a small 1,000 liters plant, it's in a lab trial plant to make a weather resistant coat that also made from the PV only. So now I just tell what are the application we are in what application we are giving the recycled PV granules. So that's the quality we are getting after recycling of the PV scrap. So that granules again we give to the company who are making this EVA or LD foam sheets. So that foam sheets are again used for cow mats. So what they are doing means like they are partially replacing the EVA and the NDP polymer with our PV compound. This is the PV compound. It's just not made with a PV. It's having a PV some EVA scrap also and some other additives so that it shouldn't stick because usually the PV granules after recycling stick to each other. So we are not doing any coating of the calcium carbonate. We are using some additives in it only so that the granules shouldn't stick together. Again, we are giving this granules to some beach sandal manufacturer, and same way they are again replacing the polymer like natural rubber or EVA or LDP for making this type of beach sandal. And we are giving to the shoe inner sole for the cushion. So usually we are giving this recycled PVB granules mostly as a replacement of EVA polymer in making the compression molding seats. And recently we developed another application. You might be knowing the temper evidence sticker. So they use a PV polymer in the manufacturing of temper evidence sticker. So we developed a special grade with the PV scrap, and nowadays we are giving not a very big quantity, like 20 tons every month we give to the company who are making this temper evidence sticker. They are replacing the virgin polymer with our recycled polymer. So now we will talk some of our partial successful projects. So the car foot mats we are making is not a fully successful project, we say. So as everybody know, the PVB get hard at the temperature less than 5 degrees centigrade. So when we supply this car foot mat in the northern part or the cool area, then it's become hardened actually. And it's getting a plasticized smell. To overcome that, we are adding some fragrances in that, but that's not a proper solution for the smell of the plasticizer. And everybody knows that the car model changes very frequently, so it's not economical to invest lots of money in the dyes because dyes are very expensive, and we are not able to recover the cost of the dye, and the people are start asking the new design there. So our partial successful project is the weather resistant coat, which we are making from the recycled PVB only. Here we are adding some additives in that, and we are cross-linking this PVB with the epoxy and some other agent. But after that also all the product is very nice. Product don't have any issue. But we are not able to successfully market it because of the competition with the big brands. And it's a solvent methanol based, and we need more investment for the development because we are not getting any funding from the Indian government for recycling or anything. It's everything we are doing at our own. So this is the main reason we are partially succeeding in this project. So now we have a targeted application with the recycled PVB. So if we make a compound, it's like in a continuous extruding. It's like when we are adding the PVB along with the epoxy, then in a continuous extruding, we can do a coating on the pipe. So that's will be one of the application, but we find that it can be very, very, very nice, where we can replace the HDP from the pipe coating. And similarly, that same product we can use for the coating on the chassis also. So epoxy role in the PVB recycling. So epoxy cross-link recycled PFilm and improve the weather resisting property because everybody is knowing that PVB film absorb the moisture and it start losing its tackiness. But if you cross-link it with the epoxy, then its tackiness improve a lot and its work in a very nice weather resistant also. And there are different grades of epoxy which having a flexible property. So if we blend this epoxy, which having the flexible property along with the PEB film, then we can find many flexible applications because the PEB film is not that flexible. So then we can find many applications like that, making the doormats, which usually means then it will replace like in a PVC in that case actually. So and epoxy improve the adhesion property also of the recycled PVB. So it can be used again as an addition to some other films. And so what I feel that the epoxy and PVB manufacturing company should come together. So the epoxy manufacturing company can suggest a special grade with the which can be blended along with the recycled PVB, and we can make different type of products. So another product which we thought can be made is a cow mat, cow or the horse mat. So this product also can be, we already have this small trial we already done. So if somebody want to come to and see in India, we are already having the small project, we have already applied this. So again, you can, this recycled PB along with the epoxy and some other ingredients you use and you can make this type of cover mats and the rubber flooring also you can do for the kids play area also. So how we can use PV films again in the making PV film, because everybody talked a lot on it. So the things the same from our side also. So means like we have to remove the fine glass powder and we have to use some special chemical. Also we are using SLS to remove the contamination of the glass or some other from the PV film scrap. But after that, it's the property get deteriorate and we are not able to give the scrap again to the PV film manufacturer. So as per us, the PV film manufacturer should come with a special grade, maybe we already talked alone on it, means like blending the PV scrap with the virgin polymer and some other ingredients, and maybe we can develop a specially grade for the, maybe for the building glass lamination, so that we feel we can use PV film screen again, making the PV film. So this is the patent we have for the process for recurving the PVB. And this is the circular economy we thought we are going to work on it. This is the windshield. So we are collecting the glass cullet. So we are getting the PVB scrap. So from the PVB scrap right now, we are making this car mat and we are making, we already on the lab plant, we are making this paint primer for the chassis coating that we are already doing. From the glass, yes, we can make the glass wool. So that process we already means like developed in India in a very economical way. If somebody want to talk on it, you are most welcome to talk on it, and we are happy to share all the know-how we have on it. So this is the circular economy model we thought, but it's not a proper model because as per us, the PVB scrap again should go for manufacturing the new windshield only, but the quality we get after the recycling of the PVB is not up to the mark to make the windshield. So now we are doing the research on the solar panel recycling. We have developed the technology for solar panel recycling, but we have not started yet the commercial recycling of solar panel because right now we are not having enough quantity of the solar panel. Maybe after 10 years, when we have the enough quantity, then we will start the commercial recycling for the solar panel also. So our goal is to work on the circular economy by recycling the scrap, going for the landfilling, and then making the value-added final products from the material recovered after the recycling. It's our prime goal. It can be with the windshield. In the same way, we are going to work on the solar panel also. From the solar panel also, we are going to have the glass, the EVA, then the silicone cells, then copper, and there's the silver. So that all things we are going to recover. Usually we try to make some final products from the product we recover. But in that case, we would like to sell the product we are going to recover from this solar panel recycling. So what the final conclusion, what we have, everybody talks same on it, that the windshield and the PV recycler in all the world, they should come on a common platform and share everybody their experience to develop a better quality of PV film from the recycling, so that again then can be used for at least for making the PV film for building glass lamination. So that's the prime focus area what I feel. And the Roman innovation is ready for all type of operation in PV recycling. So this is the things what we are doing in India and what we are looking from everybody. So this is done from our side.
Thank you very much for this presentation. Are there any questions, any comments? I have to say I like the idea of looking at the car and applying PVB again in the car. It's another way of looking at it by actually using the PVB of the car and use it for other parts of the car. It's maybe an angle we should look at also more in Europe. I don't know. I would like to have your views on this.
Yeah, means like you can again use this PVB. The epoxy manufacturer plays a very crucial role here. So the PVB is not very flexible. So if we are looking to make some seal or something somewhere, we need the more flexibility there to fix in it. So that can be achieved by the blending with the epoxy, but that process will be the continuation process. So it will not be like that we are having some granules and we are going to inject it. It will be like in a continuation injection and mixing process with the epoxy. That type of product definitely can be developed.
Just out of curiosity, how would Kurarai look at this matter?
Depends on the temperature stress.
Just a moment.
Thank you. The first thing which came into my mind is how the thermal conditions are in the car when we use epoxy and PVB at an exhausting line. Then there is a thermal degradation in the polymer or in the material, which affect the quality at the end. So, yeah, depends strongly on the application where to go. Yeah.
Any other comments from the people in the room? Baudouin?
And maybe one question, IT, you have a patent in India. Are you thinking to export your knowledge outside India? I think I understood from you that you are not able to import material from outside India to India. There is a ban for import of waste to India. But
actually, we can import the material in the form of grindings, but we can't import the scrap. So if somebody is making the flex, definitely we can import. But right now, we ourselves enough quantity in India. So, but we are happy to share our know-how with if somebody want. So we have in a very big market like China we can target, and in the Asia, Pakistan, Sri Lanka, Africa. So like the product what we are making is the cheap quality products, you can say, means like not very value added products. So the product what we are making, maybe we can't market in Europe, but definitely we can market in developing countries like Africa, Asia, so that and Latin America also. So if somebody want, we are happy to share our know-how with them. So to make different type of compounds, and then you can market that compound directly to the different type of shoe manufacturer or some other buyers.
okay, thank you. We will share your proposal to the glass recyclers within our federation. Anyway.
Thank you, sir. Thanks a lot.
And maybe to the colleagues of the plastic recycling as well at European level.
That will be great, sir.
Any last comments? No? Okay, thank you. I think we can conclude here. I think today we learned quite a lot on PVB and PVB recycling. We have heard different views and different possibilities of applications. I think that the conclusion is that we have already done a lot of work, but that a lot of work remains to be done, and that we will now have to align further to bring each other together to find solutions that can be implemented. Once the volumes are there, I think we will be able to work on it step by step, and hopefully in the coming years we'll be able to recycle also PVB and use it in different ways. So I would like to thank all the speakers who were here today and who prepared a presentation. Thank you very much for all your efforts and making, for some of you, making the trip to Rimini, and for the others for being online all the time. And apologies for the issues to get you on the Zoom call. So thank you very much. I think all the slides will be distributed normally on the Sunrise platform, so you will be able to consult them. And if you have any questions, you can always reach out to me or to any one of the speakers today to further discuss in private. Thank you for coming, and have a nice evening. Thank you. Thank you.